Tonight, we are going to stay in one place. Not a famous landmark, not a dramatic skyline, just an ordinary city street. Picture it in your mind. It is late evening. The rush is over. Streetlights cast small pools of warm light onto the pavement. A few windows in the flats above are still glowing. You can see curtains, plants on windowsills, maybe a bookshelf or two. A bus passes once in a while, then nothing for a long, comfortable moment. You might hear a distant siren, or the low hum of traffic from a bigger road nearby. But here, on this street, things are settling down. On the surface, it looks simple. A line of buildings, a strip of asphalt, trees planted in neat rectangles of soil, parked cars, a few bikes, a bin or two. Tonight, we are not going to follow the cars or the people. We are going to stay with the street itself. And then, we are going to look downward. Beneath the white paint of the road markings, beneath the asphalt, beneath the paving slabs. We will peel away the layers of this place like a cross-section drawing. We'll follow the pipes that carry water and waste, the cables that bring power and data, the tunnels that carry trains and people, the roots that quietly search for moisture and space, and the forgotten cellars and foundations that hold this whole street up. It is a tour of a city that almost nobody sees. You walk over it every day. You live above it. You rely on it constantly. And yet most of it lives in your head as a vague idea. The pipes, the cables, the sewers, the underground. Tonight, we will turn that vague idea into something clearer. Not in a frantic, technical way, but slowly, gently, like a bedtime story about infrastructure. So, if you like, you can imagine yourself standing right in the middle of that quiet street, in comfortable shoes, with your hands in your pockets, streetlights above, cool air on your face, and beneath you, layer after layer of human ingenuity. Let's start to sink through it, one layer at a time. Under the asphalt, the first thing you'd see is not steel or concrete, it's the ground itself. The road surface is usually quite thin. Below that are compacted layers of crushed stone and gravel, carefully packed to carry the weight of vehicles. Below that, the soil returns. In older cities, this soil is not the untouched earth you might imagine. It has been dug, filled, compacted, and disturbed for decades or centuries. Bits of old brick, fragments of pottery and glass, old foundations that were never completely removed, sometimes even abandoned pipes or cables that no longer go anywhere. If you could walk horizontally through this layer with a torch, it would feel like a strange archaeological sandwich. Layers of work, forgotten, then built over. Threading through the soil, you would see roots. The trees lining the street do not stop at the tiny square of soil around their trunks. Their roots spread outward, searching for water, oxygen, and space. In confined urban soil, roots often follow paths of least resistance. Gaps between stones, cracks below curbs, the looser backfill above a pipe trench. This is why you sometimes see pavements pushed upward in slow motion. A root thickens as the tree grows, and over years it gently lifts slabs and curbs. Roots can also find their way toward old, leaking pipes. A small crack in an aging drain can release moisture that feels like a tiny spring to a root system. Over time, roots can invade the pipe and cause blockages. So even before we reach the engineered systems, we have a living network that is negotiating with our construction. Tree roots quietly reshaping the pavement, testing the edges of the pipes and holding the soil together. Below the disturbed layer, as you go deeper, you reach more compacted earth, then natural rock. In some cities, the rock is hard and close to the surface. In others, the ground is softer, made of clays or sands that are easier to dig but more prone to shifting and settlement. The type of ground beneath a street shapes everything else that can be built there. How deep pipes can safely sit, how easily tunnels can be carved, how much the street may move and crack over decades. So, under your feet right now, the first system is not even human. It is geology and biology, setting the baseline for everything we place above and within it. Once you see that, we can start adding our own layers. Now imagine lowering yourself just a little further, into the layer where the fresh water mains run. Somewhere beneath your quiet street, Often about a meter or so below the surface in temperate climates, there is a pipe carrying drinking water under pressure. In many modern systems, utility guidance suggests burying metallic water mains at around 900 millimeters of cover to protect them from freezing and damage. This pipe does not begin here. It is part of a much larger network. Far outside the city, water is collected from rivers, reservoirs, or underground aquifers. It is treated to remove sediments and pathogens. It is disinfected so it remains safe as it travels. From those treatment plants, large trunk mains carry the water toward the urban area. These are wide pipes, running along main corridors and across countryside, like arteries. As they approach the city, the network branches. Trunk mains feed secondary mains, which feed local distribution pipes, which finally feed the small service pipes that enter individual buildings. Planners can arrange these pipes in different patterns. Some systems historically used simple tree-like branches, where water flows outward along dead-end lines. Others use grid or looped systems, where pipes connect in rings or meshes so that water can reach a street from more than one direction. Looped networks improve reliability. If one segment is isolated for repair, water can still flow around the loop. On your street, the main water pipe might run along one side. At intervals, smaller service pipes tap into it and head toward each building. Inside each building, there are meters, shut-off valves, and internal plumbing that splits water further into taps, toilets, showers, and appliances. But all of that depends on this buried river of pressurized water beneath the road. You don't hear it. You don't see it. You simply turn a tap, and, most of the time, clear water arrives. The pipe itself is usually made of materials chosen for strength, hygiene, and lifespan. Older pipes might be iron. Newer ones are often high-grade plastics or coated steels. Valves are placed along the network, often at regular distances, so that engineers can isolate sections for maintenance. In urban areas, guidance suggests valves roughly every block or so, letting crews shut off only a small area rather than a whole district when repairs are needed. If you imagine the city from above, the water network looks like a faint, branching skeleton. From where you stand, it is just one pipe under your feet. But it is doing constant, quiet work. Even as you listen now, it is feeding showers, washing dishes, filling kettles, flushing toilets, and topping up cisterns. And if all the taps on your street were suddenly opened, the system is designed to cope. Pressure would drop a little, but not fail. It is a background miracle, one that only really enters your awareness when it stops. If fresh water represents everything flowing toward your home, then the next system is everything that flows away. Somewhere near the depth of the water main, likely a little deeper, is a pipe that carries wastewater. Every time someone on your street flushes a toilet, empties a sink, drains a bath, or sends their washing machine into a spin cycle, water goes down internal pipes, into a building drain, and then into this shared sewer pipe. Historically, sewers have taken several forms. In many 19th and early 20th century cities, engineers built combined sewers. These were single, large pipes designed to carry both household sewage and stormwater from streets in one shared channel. It was cheaper to build one large system than two separate ones, particularly before modern treatment plants existed. When it rains, water flows off roofs and roads into drains, then into the combined sewer. In dry weather, only sewage flows. Later, as populations grew and pollution became a serious issue, many cities began to adopt separate systems. One pipe for sewage that goes to treatment plants, and separate storm drains that carry relatively cleaner rainwater to rivers or retention basins. On your particular imaginary street, the arrangement depends on when it was built and how wealthy the city is. Under older districts, combined sewers might still be in use. In newer suburbs, there may be separate pipes, one for foul sewage, one for stormwater. Either way, the direction is clear. Everything flows downhill, helped by gravity. A sewer pipe is laid on a steady slope, just enough for the water to move, not so steep that solids are left behind. Manholes appear at intervals, providing access points where workers can enter, inspect, and clear blockages. If you could float along inside, You would eventually meet larger and larger pipes as flows from multiple streets combine. When those flows reach big collectors and finally treatment plants, they are processed through screens, settling tanks, biological treatment, and disinfection before being discharged back into rivers or seas. It is not glamorous. It is rarely discussed in detail, but it is absolutely essential to public health. When sewer systems were first installed in European and American cities, they helped cut disease drastically by removing waste from crowded streets and groundwater. Today, most people only think about sewers when they back up or overflow. Heavy rain can overwhelm combined systems, causing diluted sewage to spill into rivers or even back into basements. That is why some modern projects build giant storage tunnels under cities to hold excess water until it can be treated. Under your feet tonight, though, we'll imagine that the system is doing what it should. Waste going one way, clean water going another, in two separate, hidden streams. Fresh water and sewage never meet in the pipes, but they pass close to each other, like strangers walking along parallel corridors. Drop a little deeper, or step sideways through the soil in your mind, and you may find other pipes, gas and heat networks. In many cities, natural gas is still delivered to homes and buildings through underground mains. These pipes carry fuel for cooking, heating, and hot water. The gas network has its own hierarchy. High-pressure lines bring gas from distant fields or terminals to city gates. Within the urban area, pressure is reduced, and gas flows into medium and low-pressure distribution mains, then through smaller service lines to each building. Just like water, the piping pattern can form loops and grids, with valves and regulators placed at key points. In colder countries, there is sometimes another layer, district heating. Instead of every building owning its individual boiler, a district heating system uses a central source of heat and delivers it as hot water or steam through insulated pipes to an entire neighborhood or city district. The heat might come from a power plant, a waste incinerator, an industrial facility, a geothermal well, or even large data centers that produce steady waste heat. From that central plant, hot fluid travels through a network of underground pipes, wrapped in thick insulation to keep losses low. Buildings tap into this network via heat exchangers. They receive warmth without burning fuel on site. In a cross-section of the street, district heating pipes can be fairly large, sometimes bundled together in pre-insulated casings. They may run alongside water pipes and other utilities, stacked carefully to minimize conflicts. All of this creates a quiet choreography of energy, gas or heat flowing in one direction, waste heat being recovered in another, valves, sensors, and control systems adjusting flows as demand rises and falls through the day. From above, your street looks sleepy. From below, energy is flowing in carefully controlled channels, keeping homes warm, stoves lit, and showers hot. Now we descend into the world of electricity and communication. In some cities, power lines are still mostly overhead. Poles and wires carry electricity along streets and over rooftops. But in many dense or modernized urban areas, a significant portion of the power distribution network is now buried underground. There are reasons for this. Underground cables are protected from wind, ice, and falling branches. They remove visual clutter from streets. They reduce the risk of vehicles colliding with poles. The trade-off is that they are more expensive to install and, when something does go wrong, harder to locate and repair. A break in an underground cable can take longer to diagnose and fix than damage to an overhead line that is clearly visible. Beneath your feet, you might see several layers of cables. Lower voltages for local distribution, perhaps bundled together in ducts. Higher voltage feeders, thicker and more heavily insulated, running in dedicated trenches. Alongside them, or in separate conduits, you find the communication networks. Fibre optic cables, thin and glassy, carrying pulses of light that encode data. Copper cables for older phone services and some broadband. Coaxial cables linking television and internet systems. These fibre routes connect to cabinets at the surface, to manholes where cables are joined or split, and onward to exchanges and data centers scattered across the city. If you could slow time and see the signals moving along these fibers, the effect would be astonishing. Messages for friends, video calls, streaming films, work files, payment transactions, sensor readings from distant machines, all of it pulsing through hair-thin strands beneath a quiet bit of tarmac, at almost the speed of light. Those signals do not stay local. The fiber beneath your street links into larger backbones, which run to national and international networks, including massive subsea cables resting on the ocean floor. You might think of the internet as a cloud, floating in the air, but a huge portion of it is routed through very physical, very grounded cables like these. Above, someone is scrolling on their phone in bed, perhaps even listening to this narration. Below, the phone's signal travels through a chain of radio links and fiber segments, threading through ducts and splice enclosures in the soil. Electricity and information, side by side, feeding a modern street. Now we go deeper still. Under some streets, you eventually reach a large hollow, a tunnel. In cities with underground rail systems, these tunnels carry metro trains, trams, or regional lines. They might be cut-and-cover tunnels sitting just below street level, or deep bored tunnels passing far beneath basements and older pipes. The idea of running trains underground goes back to the 19th century. London opened the world's first underground railway in 1863, using steam trains in tunnels dug to relieve surface congestion. Later, electric traction allowed deeper, cleaner networks to grow under many major cities. Over time, metro systems have expanded into vast hidden networks. They weave under rivers, rise up to meet elevated sections, loop around city centers, and stretch out into suburbs. From your quiet residential street, you might not even be aware that a train passes below several times an hour. Yet down there, behind thick tunnel walls, trains carry thousands of people daily, guided by signals, monitored from control rooms, and supplied with power through third rails or overhead lines. These tunnels are more than just tracks. They also carry drainage channels, emergency walkways, communication cables, and ventilation ducts. During heavy rain, water can seep into tunnels through small cracks. Drainage systems and pumps work constantly to keep them dry enough for safe running. In newer lines, platform screen doors, fire-resistant materials, and flood barriers are designed into stations and tunnels to manage risks like smoke, heat, and inundation. Sometimes, besides metro tunnels, there are utility tunnels, corridors dug specifically to carry bundled pipes and cables that need to be accessible for maintenance. In some cities, engineers create multi-purpose underground corridors where electric, telecom, water, and district heating lines run together in a manageable environment, away from street-by-street digging. Farther out, big road tunnels carry motorways under rivers or dense districts, reducing surface congestion. All of these larger tunnels share the underground space with the smaller utility trenches we have already visited. The planning to keep them from colliding is intricate. Engineers must map clearances, layering, and safe distances between gas lines, electrical cables, water mains, and railway bores. Standing back in your mind, you can imagine a side view of the city, layers of lines and voids, like a complex musical score beneath the pavement. Between the busy world of pipes and the deep world of tunnels, there is another kind of space, basements and cellars. The buildings along your street do not float. They stand on foundations that spread their weight into the ground. In older blocks, there may be stone or brick foundations resting on compacted soil. In newer structures, reinforced concrete footings and piles transfer loads deeper. Above those foundations, many buildings extend downwards into basements. These underground rooms can be simple storage spaces, boiler rooms, car parks, or fully finished living areas. Historically, cellars stored coal, food, and goods. In some cities, networks of interconnected basements and service tunnels grew quietly behind the facades, allowing deliveries, laundry, and maintenance to move out of sight. Over time, some of these spaces are abandoned, partially filled, or forgotten. Their outlines become ghost shapes in the underground plan. If your street is in a very old district, you might find layers of history beneath a present-day shop. Old vaulted cellars from centuries ago, bricked-up doorways, remnants of earlier street levels. Elsewhere in the world, entire underground districts have been intentionally built. In Montreal, for example, the so-called underground city is a network of tunnels and indoor complexes linking offices, shops, metro stations, and public spaces, stretching for kilometers beneath the central business district. It connects more than 1,000 shops and multiple metro stations, giving people a climate-controlled way to move and spend time during harsh winters. In Helsinki, Hong Kong, and other cities, planners have also used underground caverns and tunnels for shopping centers, swimming pools, reservoirs, and waste treatment, freeing up surface land and improving resilience against weather and climate impacts. Under your imaginary street, we will keep things modest. Perhaps there is a line of basements, resting above pipes and ducts. Perhaps there is a small shared underground car park, its ceiling just under the road, its columns threading between utility corridors. These human spaces are part of the underground fabric too. They are where we interact directly with the below-ground world, parking, storing, repairing, and occasionally sheltering. So far, we have talked about what is built under your feet. But there is also the question of how it is maintained. In many older cities, records of underground utilities are a mixture of careful engineering drawings, hand-marked updates, and in some cases, educated guesswork. Original plans might have been drawn on paper. Street works over decades may or may not have been properly documented. Different companies and departments may have their own maps. Modern projects increasingly use digital geographic information systems to map pipes, cables, and structures in 3 dimensions. But even then, ground conditions and historic surprises can make reality more complex than the drawing. Imagine for a moment the daily routines that support this hidden city. Early in the morning, a crew opens a manhole and lowers a camera into a sewer, checking for cracks, roots, or blockages. Later, another team carefully digs a narrow trench to replace a leaking section of water main, closing valves to isolate the affected segment while keeping most of the neighborhood supplied. Elsewhere, technicians pull new fiber optic cables through existing ducts, using winches and lubricants to slide glass strands hundreds of meters underground without breaking them. Further away, a maintenance team walks a metro tunnel during night closures, checking rails, signals, and drainage pumps. On a different day, a tree specialist inspects street trees, measuring growth, checking root space, and advising on where root barriers or structural soils might be needed to protect pavements and pipes. These activities are seldom visible to residents. Sometimes you see a work crew and some cones. Sometimes you notice a temporary patch of new asphalt or a metal plate covering a fresh dig. But most of the time, the underground city is maintained with minimal disruption, as quietly as possible. There are also rooms above ground where the underground is monitored. Control centers where water networks are tracked through pressure sensors and flow meters. Electric grid control rooms where operators can see which cables are live and where faults occur. Rail control centers where every train's position in the subway is watched on wall-wide diagrams. From these rooms, decisions are made. Which valves to close, which route to divert power through, which pumps to start, which signals to repair first. The systems under your street are not just physical objects. They are part of monitored networks, woven into software, communication links, and human routines. For the most part, the underground systems we rely on are designed to be robust. Pressures are managed. Materials are chosen for durability. Backup routes exist in water and power grids so that if one line fails, another can pick up the load. But no system is perfect. Sometimes, and perhaps you have experienced this, the hidden city under your feet makes itself known in dramatic ways. A water main can burst, sending a fountain of water into the air, undermining the road surface and flooding basements. A sewer can become blocked, causing waste to back up into homes or manholes to overflow during storms. A gas leak can create dangerous pockets of flammable vapor, leading to evacuations or, in rare cases, explosions. Electric cables can fail, causing power cuts. Overhead lines might fall in storms. Underground cables might fail silently and take longer to diagnose. Stormwater systems can be overwhelmed by extreme rainfall, particularly in cities that still use combined sewers. This can lead to overflows into rivers or onto streets. Some cities have responded by building deep storage tunnels or retrofitting green infrastructure, such as permeable pavements and rain gardens, to absorb more water before it reaches the pipes. In some regions, aging electric cables have leaked insulating oil into soils and groundwater, creating slow, invisible pollution that must be monitored and cleaned. Major metro systems face their own vulnerabilities: flooding in tunnels, signal failures, or structural problems that require sections to close for repairs. When any of this happens on a particular street, life above is briefly disrupted. Roads are closed, traffic is diverted. Residents may be without water or power for a while. Engineers arrive, dig, pump, repair, replace. It can feel chaotic and inconvenient. But behind the drama, there is usually a well-rehearsed sequence. Isolate the fault. Make things safe. Carry out the repair. Restore service. Then, perhaps later, reflect on how to reduce the chance of it happening again. As climate patterns shift, many cities are updating their underground infrastructure to cope with heavier rains, higher temperatures, and sea level changes. New tunnels and drainage systems, upgraded pumps, more resilient materials, and smarter monitoring are being adopted gradually, street by street. The street you are standing on in your imagination may have had a dozen such incidents over its lifetime. Each one leaves a subtle trace: a newer patch of asphalt, a slightly different manhole cover, a record in a maintenance log. The underground city is not static. It evolves. So far, we have treated underground space mostly as a technical zone: pipes, cables, tunnels, foundations. But planners and architects are increasingly thinking of the subsurface as an extension of urban life. In some cities, master plans now include explicit underground layers. They identify zones for transport, for utilities, for commercial spaces, and even for public amenities below ground. There are reasons for this. Surface space is limited and contested. As populations grow, it becomes harder to fit everything at ground level: roads, trams, bike lanes, parks, housing, shops, trees. By moving certain functions below ground, cities can free surface space for people and green spaces, while protecting sensitive infrastructure from weather and accidents. Helsinki, for example, has an underground master plan that uses caverns carved into bedrock for data centers, sports facilities, and storage, connected by utility tunnels and protected from harsh winters. Montreal's underground complexes show how retail, offices, and transit can be integrated into a climate-controlled indoor network that people use as naturally as they use surface streets. Future proposals imagine underground cities, where transport systems, utilities, logistics hubs, and even agriculture share deeper levels, leaving surface streets quieter and greener. Some designs talk about earth scrapers that go down instead of up, stacking uses beneath plazas. Others propose extensive networks of utility corridors that can be walked and worked in without constant surface excavation. At the same time, there is growing awareness that underground space must be planned with people in mind. Light, air, orientation, and psychological comfort all matter. Nobody wants to live in a city where being below ground feels oppressive or confusing. So architects experiment with skylights, light wells, reflective surfaces, art, and wayfinding in underground spaces, making them feel as considered as any surface street. For the street in your imagination, the future might mean upgraded sewers and drainage to handle more intense storms, new district heating pipes fed by renewable sources, replaced electricity cables with safer, low-leakage insulation, additional fiber ducts for ever-growing data needs, better root space for trees using structural soils and planned utility corridors. perhaps a small new utility tunnel, letting future crews access multiple services without constant digging. On the surface, you might notice only subtle changes: fewer overhead wires, more trees, quieter, cleaner air as some traffic shifts to underground rail or tunnels, occasional new access hatches or discrete ventilation shafts. The underground city does not seek attention. It simply adapts to support whatever life above requires next. Let's return now to where we started. You are back on the quiet street. Streetlights glow. A distant rumble of a train, maybe just your imagination. A faint vibration underfoot as a pump starts somewhere, far below. You know, now, that under your shoes there is a layered world, roots exploring soil, foundations holding buildings steady, pipes carrying water in and waste out, gas and heat piping energy around like warm blood, cables pulsing with electricity and information, tunnels with trains sliding through in the dark, basements, service corridors, and human-made caverns, sensors, valves, switches and pumps quietly doing their work. Every ordinary street in a city is like this. Even simple corners that nobody photographs are supported by huge, invisible systems. The next time you walk down a road at night and everything feels calm and effortless, you can remember this hidden choreography. There is something reassuring about it. Thousands of people, over many decades, worked out how to move water, waste, energy, and people safely through difficult spaces. They made drawings, dug trenches, laid pipes and tracks, tested materials, improved designs. Others maintain and upgrade those systems, often without you noticing. It is not flawless. Sometimes things break. Sometimes plans fall behind reality. But underneath, there is a continuing, collective effort to keep your world functioning. So, as you rest now, you can picture your own street, or any street you know, from a new angle. Not just facades and traffic, but layers of cooperation and engineering under your feet. If your eyes are growing heavy, you can let go of the details. The exact names of pipes and systems don't matter. What matters is the feeling that, beneath the everyday noise, there is a structure, a kind of quiet, human-made root system, carrying the flows that let you live, work, and sleep. You are held up by rock and soil. You are served by networks that never sleep. You are part of a city that extends not just upward and outward, but downward too. And tonight, you have taken a slow, calm tour through that hidden world. You can come back to this street whenever you like, in your imagination. Stand still, take a breath, and remember, there is an entire city under your feet, quietly at work, so that you don't have to think about it at all. You can let it carry on down there, and you can rest up here.